Good afternoon, everyone. I'm Natalie Piperidis, and it is a real pleasure to welcome you all today for our webinar. Whether you're joining us from nearby or from across the globe, thank you for taking the time to be here. I would like to begin by acknowledging the Aboriginal and Torres Strait Islander peoples of this nation. We acknowledge the traditional custodian of the land on which SRA is located and where we conduct our business. We pay our respects to ancestors and elders, past and present. Today's presentation will run for approximately 45 minutes, followed by the Q&A session. This afternoon, we have a fascinating topic that's gaining popularity and sparking growing scientific interest due to its promising new application. It's generating a wave of excitement in the research community, and the pace at which this field is evolving is truly remarkable, unlocking innovative possibilities that were once thought to be out of reach. It is my pleasure to introduce our speaker, Joel Simpson, who will be sharing his insight on NIR current and future development. If you ever wanted to understand the full story behind near-infrared technology in the sugar industry, you are in the right place. I feel very privileged to introduce Joel. He has been an integral part of the SRA NIR team for the past 17 years, ever since completing his bachelor's degree in chemical engineering at the University of Queensland. His works focus on developing, optimizing, and maintaining a wide range of NIR applications tailored to the needs of the sugar industry. Interestingly, a younger Joel once dreamed of becoming a planetologist, but luckily for us, he turned his focus towards sugar instead. His dedication is truly exceptional. He's on call 24/7 during the crushing season, and it's not unusual for him to be troubleshooting mill issues at 3 a.m. and loving it. Joel's passion for NIR is so strong, he once explained it in great details on a first date. Fortunately, his now wife completely understood, summing it up perfectly. She said, "So you shine a light on the cane and it tells you how much sugar is in it." That's, to me, is a true soul of a scientist. So without further delay, Joel, the virtual floor is yours.
G'day, I'm Joel Simpson. I'm a NIR Support Engineer for Sugar Research Australia, and I'm here to talk about all things NIR in relation to the sugar industry and what we're currently doing and what we are developing for future applications. So, what is NIR? Spectrophotometry or spectroscopy is another name, but basically it's using light directed at a sample that measures a spectra in the near-infrared range, wavelength range. So that makes it a secondary method of analysis. So this is typically, you have to have a primary laboratory method of analysis that correlates to the secondary analysis via the spectra. So this makes it a rapid, non-distractive analysis. So that aspect of it makes it pretty handy. So then after you get that spectra and the laboratory analysis, the primary method, you then develop an algorithm to develop a relationship between the spectral chemical signature in the spectra and the corresponding laboratory results. So this allows you also to be able to do multiple primary methods at the same time if you've got calibrations for them. So you do one scan, you get multiple results for all the things that you've got calibrations for, which is quite handy. So how does this actually work? So traditionally, well, an easy way to explain it would be to say, I'll just see if I can get yep, there we go. You have the instrument and it shines a light on the target sample, and the molecules in that sample either absorb or reflect the light and the energy of the light coming back. We look at the difference in the absorbed energy that the molecules absorbed versus what we get back, and that's how we generate the spectra. So the other way to look at it is the light coming back, that is the absorbed the light minus the absorbed light. It then gets split into either via diffraction grating or a prism, or there's a few different ways to do it. And it gets split into different wavelengths, like you'd see in this prism here. The only difference is that the NIR region is the other side of the visible region. And also on the other side of the NIR region is the infrared. That's why it's called NIR, near infrared. Not quite infrared, but above visible. So that's kind of how it works. And you have a detector basically to collect the wavelengths for that spectrum. So basically the way we build calibrations from that is we get the spectral scan. Actually, that's an example of a sugarcane spectra there. And we get the laboratory result that corresponds to that same sample. So this would be the sample here. In this case, it's a cane stalk sample. And then we do that lots and lots and lots and lots of times. And then we input that into the computer and use a statistical technique. So it's either principal component analysis, partial least squares, support vector machines, lots of different ways you can develop the calibration. But yeah, you use the maths to develop the calibration to give you an algorithm that relates those two components. So then when you see a new sample, you can predict what the laboratory result would be via the spectra. And that's the essence of making calibrations. So what are the advantages of this? So the speed of analysis allows you to do allows you opportunities with things that you couldn't do in using the traditional laboratory methods. So a good example would be fiber. The fiber test takes 3 hours in the traditional laboratory method. NIR scans every 7 seconds. So you wouldn't even be able to represent a consignment at that rate of 3 hours, but at 7 seconds you can see the variation within the consignment. So it's quite an advantage. The other advantage is like, so for example, molasses. The time factor means that in the past, the time of the test would be longer than you'd be able to do something with the information. So it tells you what you could have done if you had the chance. But with NIR, doing the same technique, you get a result in a time that you can actually do something that matters and influence the process before it becomes a problem. So yeah, the other opportunity of the rapidity of the method is that you can represent a population a lot quicker and better by just the sheer number of samples you can, because you can sample it more frequently. So yeah, that's a huge, you can do a lot with that. And the other factor is that is also another time-saving thing, is that it provides all those results simultaneously. So instead of having to go do a laboratory, do a fiber test, and then do a polarimeter reading, and then having to do the bricks, and then do all these separate methods that all take time by themselves, every 7 seconds, boom, there's your result for all of the 30 odd things we have calibrations for example, in cane. So this is a non-destructive method. So it means that you can measure it in situation. So in situ, so for example, you can measure it in paddock in the field. You can go up to a cane stalk and measure it directly without having to cut the stalk or remove it, which means you can do a lot more scans than having to put it through the small mill. And also the fact that you get such a large data set so quickly using this rapid technique means that you can start looking at your data and developing bigger picture concepts, such as the maturity model, which I'll talk about later. But yeah, you can really step back and start looking at what can we do with this data, because it's not just about generating the data, it's what you do with it that matters. So new calibrations, well, there's also a thing called spectral, well, you can basically go back into spectral legacy is the word I was after, sorry. You can go back in history and look at scans that you've previously collected. And if you've got a new calibration for something new that you've got suddenly a new measurement that you wanna see what happened in history, you can actually take that measurement, back predict on all those spectra that you have that you want to look at, and get predictions for things the scans that are long past in history. So it's quite useful in that regard as well. And the other thing that we tend to do is always trying to improve calibration performance by building in new data as it comes along. So if there's some other factor that we need to consider, we can include that and get a better model and get better predictions. What are the limitations? We talked about the benefits. What are the limitations? So the key one would be that the error that's in the primary method is inherently built into the NIR calibration. And you can get an idea of what that error is by doing duplicate samples in the lab to see what the primary method error is, and then gives you an idea of what your NIR error is compared to the lab method. But I guess the counter to this is that this error is pretty quickly accounted for by this increased representation. So yeah, if you've got a method that you can't even give to every consignment, and suddenly you can give a result for every 7 seconds, that's a clear advantage, even with a little bit more error due to the NIR and the primary error being added on top of each other. But I guess the other factor is that the calibration equation really depends on the performance of the calibration depends on the quality and the quantity of the data you've got. So if you've got poor data, so rubbish in, rubbish out, that's a pretty common phrase that we use in NIR. But that also comes to, there's another subtle thing on that. Sometimes the chemical signature is so if you've got like a parts per million thing that you're trying to measure, it's a bit trickier to tease that information out of the spectra. So that's another factor you've got to consider. So more concentrated, the bigger chemical signature in the spectra, the easier it is too. So that's another factor. But generally, population, just more samples is the way you deal with it and let the math sort it out, basically. So the other factor that limits what you can do with NIR would be the range of the calibration. So if you have your calibration population is based off the NIR and the laboratory method. So if your calibration happens to have a set range in that population, then if you try and predict something outside that range, you're now extrapolating. And here be dragons. It's questionable as to what the error is when you get outside the range of a calibration. So that's another restriction you need to consider. But the other thing that can be seen as a negative, but I actually see it as a positive, is validation is still required to ensure that your NIR predictions are matching up with reality, with the laboratory results. I'll cover that a bit further in another slide. Well, this slide actually. So here we've got 3 different scenarios. You have one population that has poor accuracy and poor precision. That's like a method you're trying to measure something. It's got poor accuracy, poor precision. Think of it like you're shooting a bow at a target. And then you have poor accuracy and good precision. And this typically is actually what NIR looks like. So it's very tight, but it's not necessarily lining up with reality. And what you'd hope a lab would be good accuracy and good precision. So that's right on the middle of reality. So how do you bridge these two? How do you get NIR to basically move into the center? And that's a process called validation. So here's an example. So basically what you do is you get, when you're predicting with NIR, you want about 10% if you can of validation data. So that's where you've got the laboratory and the scan results. And you do that to see what the difference is back on that precision, what the distance is between these two. And then basically you're correct for that, and that brings it in line. So this one could be in a line this way, like so if it was parallel, but the population was offset, then you basically add or subtract the difference, and then that brings you in line with reality. So that's what a bias is called, if you ever hear that. So the bias is how much you need to apply an offset to line up with reality. It should be lining up with 45 degrees. Oh yeah, sure. I should point out what this graph is. This is a validation plot. So on the bottom, you've got the laboratory result, the primary data, and on the other axis, you've got the NIR data. And ideally, it should be on this 45-degree line. So if it's calibrating well, it should be right up on that 45-degree line. If you have slope, then that's an issue that you probably need to recalibrate for. But bias, if it's off, if it's like this in parallel with that line, but not on the line, then bias is how you correct for that. The other factor is if you have a small validation population, obviously your the accuracy and what you can take from that information is not as much as if you had a bigger population. So that's another thing to consider. And the other part of what you look at for validation is the width of that cloud. So how broad is this cloud? In relation to the error of the laboratory equivalent, just on the duplicate laboratory results. So use that, and then if it's all within limits, then we're good. If not, you might need to take some action. So that's good to do 10% of validation just to make sure that we're lining up with reality. But the other 90%, you just do the scan. You don't need to do the laboratory result. So that's really where the saving is. It's in that 90%. So don't focus too much on the 10%, although it is a bit of work. The 90% is where you get the value. What applications have we already applied for this technology? At the moment, we started actually with process instruments with prepared cane, but we also now do sugar, bagasse, and mill mud. So that's these instruments up the top here, the Profos, the PAT-U, and the Perton online system. And then we also have laboratory instruments now. So that can basically you take a sample to the instrument. So these online ones are on the side of a process. They live on the mill. So for example, number one mill chute, and everything that comes past it measures. The laboratory instruments are a bit different in that you have to take the sample to the instrument and take a measurement, which is a lot slower, but it does give you flexibility. So now you can look at more products. So this is particularly useful in mills where you have lots of different intermediate products like bagasse and massicrete and magma and syrup and juice and molasses. All these things you can take to the instrument and get a result and take an action in process with that. So we've got the FOSS DA and the Perton lab equivalent. And now we've come into new technology. The new kid on the block is this micro NIR, which I've got one here. I don't know if you can see that. Yeah, and we because it's portable, so instead of having to bring the sample to the instrument, now you bring the instrument to the sample. So that means that you can do things like put it directly up against a cane stalk and measure maturity. You can take it to mill mud and see what nutrients you have in that out in the field. You could also potentially use it for soil. And we've also looked at cane leaf, but these are just the start. So basically, you've probably got by now that if you have a sample that you're interested in and you have a technique that you have well established in terms of a laboratory method, and you take a scan of that sample and you do that enough times to develop a calibration, then that suddenly, if there's a chemical signal and you've got enough population, you can have a calibration and start predicting with the instrument. And I guess the other instrument that's actually predates all of these is the SpectraCane, which is largely used in the breeding program of SRA, and that has a Dedini that crushes cut a grinder that crushes up the stalk and then prepares it so that you can measure all the usual suspects, pole, bricks, fiber, and then relate that to what the variety that you're putting through is to assess how its performance is in terms of variety. Composition performance, I guess. So going back to the start, so the process instrument, the most common one is the CAS, the cane analysis system, but we also have the SAS for sugar, bagasse, BAS for bagasse, and MAS for mill mud. But so going to the CAS, that's often used for cane payment inputs. So if it's not CCS, pole, or bricks, at least typically fibers used because, again, the 3-hour test problem. So yeah, it depends on the cane payment agreement, of course, of the area. The other useful thing that an online system can do is process control. So that means you can make adjustments. So if you've got a CAS and a BAS, you can make maceration control decisions, and you can also calculate live extraction, all that sort of thing. But also see what's coming in. So even in a BAS by itself, if you see there's a high lot of a lot of moisture coming through the gas, then you can give warning to the boilers that there's some high moisture coming through, and they can make associated adjustments for that. So these particular instruments, they operate on a 7-second scan cycle, so that's pretty quick. So you see a lot of data. I think we get about 10,000 scans a day per system, and yeah, so that's running all year round while the season's running. So that's a lot of data to handle at the end of it. So the way we link this data to give it meaning is we link it to consignment via a unique sample number, and that's via a mill tracking system. I guess the key thing with that is that we want to be able to remain independent. So we just get this number and we don't know whose it is. It's just a number that we know is that's a consignment, but we don't know whose it is by that number. So that's useful for us. We're basically blind. We don't know whose cane's coming in, but we can give you the result without any sort of outside influence, which is a good system, I think. So there's a few ways to screen. Obviously, if you've got something in process and the the hopper that the cane or whatever you're measuring in is fluctuating, so sometimes it might be too low for the sensor. You want to be able to reject air because you don't want to pay on air. So yeah, we have a height sensor. So if that comes through and we say there's nothing there, then we don't scan. The mill stopped, we don't scan because it'll be the same sample all the time. And there's another method that we use to discriminate when we don't want to scan something, and that's a statistical method called Mahalanobis distance. I'll go into that a bit more in the future. But yeah, this data that we generate is owned by the mills, but we have permission to use it for calibration and validation, and also just to look at bigger picture ideas as well. So this is an example of one product. This is the most developed one in terms of the CAS. But this is what we measure every 7 seconds on a mill typically. Not all these are reported, and not all of them are created equally. Some of these don't see much validation because the method takes a lot of, or costs a lot of time, costs a lot of money. But we have got it there to give us an idea of at least a relative measure to see how things are performing. Like a good example might be ethanol. We don't validate that very often, but it is still useful in telling us if, say, fermented cane's coming in, we generally see an ethanol spike when that occurs. But yeah, we tend to validate. The more value you have in the data, the more you'll validate. So the bigger the population of your calibration, the better the prediction error. So I did mention that I was going to talk about Mahalanobis distance. So basically, just a statistical method to compare the scan you're looking at to a library of known good scans. And then you look at a statistical difference from that library, and it's basically a standard deviation. And then if it's more than 3 from the average, then that is an outlier. That's probably air. It's probably steel, something that's not cane. So you want to reject that because you don't want to predict on that. The other alternative is sometimes you get NH outlier that is compared to the nearest neighbor, the distance to the nearest neighbor. And that is more of a contender that we might consider adding to the library. So that could be you've got some new sort of mud that we haven't seen before. And it's a little bit different, but it's still cane. And that's one that we'll add to the library if you ever heard that before. That's what we're doing, just trying to make sure if we see that again, it's still cane, we don't want to reject it. So there's a bit of that that we do as well in terms of screening good data from bad data. All right, going on to the laboratory NIR instruments. So I mentioned that you can basically, they're pretty flexible because you can measure more different products. So it's quite handy in a mill. When you're just looking at process control, you need to make decisions. That's what you use it for typically. And to do that, to be able to handle all those different types of products, you need to have different ways to sample it. So for example, for juice and syrup, you have to use this thing called a gold reflector. And that just plonks down, you put the sample into the small cup, you plonk down the gold reflector, and that limits the path length to try and counteract some issues with the water peak. That is a problem for NIR in general. So that's a way to deal with that. But also, fiber is better to pack in the bigger a bigger sample cup. So things like bagasse and prepared cane, that's something you'd use for that. So across them all, you can do most products that we are interested in. And it's another case of if you're interested in something new, you do that analysis, scanning procedure, build up a calibration, and then yeah, then you can use it as a prediction. So the other advantage is like there's a fair bit of staff turnover in laboratories in the Australian sugar industry. So it's quite handy to have a system that you basically just put the sample in the cup, put it in the place where it's got to go, and press the button, and it gives you the number you're after. So pretty minimal training. And usually the sample time, depending on the absorbance of the thing you're measuring, varies between 30 to 2 minutes, 30 seconds to 2 minutes, sorry, 30 seconds, not 30 minutes, to 2 minutes. So it's still pretty quick, not the 7 seconds, but it's quick enough that you can take a sample to it, get a result, then go off and make a change. So yeah, but I guess another thing that you need to consider is that validation is still required. We still need that 10% just to keep it honest, basically. So now moving on to the new kit on the block, I've got one here, a Viavi Micro NIR. It's a handheld, as you can see. Basically looks like a torch. Quite handy because you can actually take it up to things and take up the things you want to scan and collect a scan. Same principles of NIR. If you get a sample and you get the lab results, do it lots of times, make a calibration. So that's what we've been working on recently, or one of the many things we're looking on recently. It uses a variable filter, linear variable filter. NIR, that's just the type of data collection it uses to get the spectra. But that's the reason why it's so small. It uses a different method. And it uses Bluetooth to talk to a laptop or a tablet or mobile phone. So you basically operate, you use this, there's only one button on this. So you use that to collect the scan. There's a little reference you got to do before that, but all the results go to the laptop or tablet. And again, like all the other instruments, multiple calibrations we're developing for different products and also different constituents for both in the field and in the factory. Yeah, it's early days, but there's lots of things that we're going to be using this one for. The primarily one that we've working on most recently that has the most mature calibration for this would be the cane stalk maturity calibrations. So what's that? What's sugar cane maturity? Well, with all the other bigger picture sort of advantage to having a big data set because we've got this NIR system in a lot of different mills all around the world, a lot in Australia as well. What that does is we can look at that and look at, well, what's the fundamental nature to cane? So one of the fundamental things of cane is that if you plot a ternary diagram, so what's that? That's this equilateral triangle graph you can see here. So basically any point on that graph between these three different components is 100. So so the three components would be moisture, so water, insoluble solids, which is fiber, and then soluble solids, which is bricks. So if you know so we basically plotted all of the data we have on to a graph like this. This isn't the actual graph. This is just a validation plot. But we plotted all on a graph like this. And from that, we developed a model, which is the red line, basically. And from that line, we could determine that there's actually a peak, an optimum sucrose production point, which is between 65% to 70% moisture. And yeah, that's the optimum time. That's when you want to be harvesting in that window. If you hit below 65, then you're probably starting to ferment. And if you go before 70, then you're immature cane. So I guess that's the other feature. This line represents the two main metabolic reactions that occur in the plant. So the first part down here is actually the growth phase, where you're making cellulose. So there's a metabolic reaction creating cellulose, making more plant, basically making the cup bigger. And then the second part is where we start to stress out the plant in terms of moisture. It's getting thirsty. So it says, oh, I need to prepare myself for a rainy day. So what I'm going to do is I'm going to store some of my energy in the form of sucrose. And then that's where we have the sucrose production reaction. And so that's really what the curve is modeling. But what that means is it tells you where you are. If you can measure that at any given point, you know where you are on that curve. You can make a decision as to, oh, do I irrigate to basically move it back along the curve, or do I, if you're in a certain window, you could apply modus. That's another decision you can make. Or it even could be something like, I'm going to take this paddock over this paddock because it's more up the line than this one. I guess the other factor that's involved in this graph is if you know one of these three components, then you know the other two. So you just pick the cheapest one to measure, which is Brix refractometer. So that's this one. So we basically make a calibration using the model and that measure. So that's what we talk about when we're talking about the maturity model. So we got the handheld NIR and we got a dibbler, which is actually one of these things. I don't know if everyone's seen one of these before. It's a little spike. You stab it into the cane stalk and you collect the juice, put it on a refractometer and take a Brix reading. So we did that for a range of maturities. We actually had to, we did start this last year, but we caught it a bit too late. We did it started in April, and it was already too mature. So we had to restart it again this year in January, and we caught the other tail. So we've got a nice calibration population now for the range of maturity that we're looking at. But the other thing we did to develop the range of maturities, we did every internode as well. So we stabbed and scanned every internode of stalks, and then we cut the stalk and ran it through a small mill to get the average Brix for the average of the stalk. So we did that many times, as I was talking about before, and developed a calibration. So yeah, the reason why we did every internode, well, first is to build in the variation of maturity within the stalk. But the other thing that it gave us is we asked the question, well, if we're going to use this this tool out in the field, you don't want to be scanning every single internode. What's the minimum number of internodes that we need to give a statistically relevant number? And we came up with a method that was basically we take 3 internodes from the top, from the cabbage, and scan that one, 3 internodes from the bottom, scan that one, and then you average those 2 results. And then that gives you the best correlation to the small mill result, which is the average of the stalk, which is what you're interested in. So that's what these calibrations populations look like. They're pretty nice broad range. For a bit there, we had a big gap, so now we've filled the gap, and yeah, they're looking quite nice. I guess some other factors involved with this is when you've got this information, it gives you the ability to really look at bigger picture ideas. When you start doing sampling, you can start considering what each stage of the maturity cycle, the implications that you could play with there in terms of irrigation and modus application or any other factors that you might consider. But basically, it gives you the ability to measure something and then make an action on it. So more so other products we're looking at as well that are still being developed. So these aren't finished, but in development. Soil nutrient equations. We have done a bit of soil nutrient work on the lab instrument before, and that looked promising. So we figured we'd try and do it for the micro NIR as well. And the real advantage to NIR is whenever you're doing a sample anyway. So if you're doing a soil test and you've got to pay money for it, you might as well take a scan as well to see if you can build a calibration. So that's really what this is. We're going to be getting our NIR, micro NIR, and taking it with us to where we got the soil collection, and that we'll get a soil test on. And also, we're going to be scanning inside a bag, a sample bag, so directly on the sample. Problem with that is you got to clean it. So we're also scanning through a set bag, so it's got to be the same type of bag. But building in the bag signal and the soil into the equation, so that way, so long as there's not too much error from the introduction of the bag, we can really simplify the sampling procedure, and also so you won't have to clean the instrument every sample because you're hitting with dirt basically. So yeah, that's our work that's happening this year. Another similar project, also looking at nutrient, is Project Julian's working on this year, relating mill mud Also looking at ash. Ash might be a trick because I know spectrally ash diffuses light, so that could be challenging, but the mill mud will work because we've already got a very similar instrument basically. It's a PAT U, which is the same Viavi linear filter instrument that is the process version that lives in Tully Mill at the moment. And that's on the mill hopper, and that works quite well in terms of using it for mill mud. So we'll be comparing the two between each other and also looking at some other implications in terms of nutrient management that Julian's looking at. Another uh, aspect that we've been working on for this handheld instrument is that we've developed a calibration, what's called a classification calibration. So it's a discrete calibration. It is used not to give you a number per se, but to tell you this is in a particular group or not, a classification. So we've done that for products. So you point the NIR at a particular product. Say if you use the same NIR for a range of different products, it can tell from the spectra which product it's looking at and then use the associated calibration. So that's where we're hoping to head with it, but that will require some software alterations to be able to do that. But the calibration already exists and works quite well. So that brings us on to software development. So we're currently looking at rewriting the online NCS3 software for the CAS, but we're also going to be looking at the lessons from that in applying a very similar sort of prediction engine to use it for the handheld micro NIR as well. So currently the micro NIR uses a laptop to scan. It can use a mobile, but it's kind of the app's not really. It should be getting an update soon, but ultimately we want to be able to do more things than I think the app will be able to do. So we'll be developing our own app to just make it a more portable system. So you've got a mobile phone, have the handheld NIR. You take a scan, it goes to a central SRA hosted public facing server, maybe something like SPIDNet, if not SPIDNet. And then you get the prediction engine from that, and that goes to the app. We could also look at introducing things like GPS of the phone when you take the sample, so that way you can see where in the paddock you were when you took a scan. That sort of stuff gives us potential. Still in development, but that's what we're looking at doing. So now going on to a specific issue that we've noticed with the online instruments, so the CASs. We noticed that there's a problem specifically with fermented cane. So what we want to do with this project is to improve the pole prediction accuracy when fermented cane is in the supply. Because we basically identified that there's an issue related to fermented cane and pole. This issue doesn't occur when there's healthy cane present, only when we've got some fermented cane in enough quantity that it becomes an issue. And we have developed alternative methods in the past to try and deal with this, such as ethanol equation, as I mentioned before, or the pole to sucrose ratio equation, but these require post-processing calculations, and they're difficult to implement and validate. So they were never really ideal. So we needed a different method. So let's just define what fermented sugarcane is and how it relates to maturity. So basically, I mentioned it before, but the further you are less than the 65% moisture, the more fermented you likely are. So that's one way to look at fermented cane. So basically, you're drying out too far, and now the plant's given up and dying. But another problem that complicates this whole thing is that suckering is basically new growth that comes off. So you've got some that are well off the maturity curve, as well as some cane that is on the same plant that is right at the start, new growth at the very start of the cellulose production phase. So really makes it very difficult to model. What are the causes typically for fermented cane? So typically things like cyclones, floods, and frosts, all of which we've probably seen a bit too much of recently. Over mature moisture stress canes, that's really about the maturity model. And cane supply, like delayed crush cane, pest diseases, weed competition, standover cane, and 2-year crop cycles, and other factors. But there's many different ways to get to fermented cane. It's basically when the crop's in trouble. So here's where fermented cane fits into the maturity model and also why it's so difficult to model. So I talked about the cellulose production phase, which is this green line here. So that's consider that to be a reaction. The cellulose reaction, that would be the sucrose production reaction. But then after you get to 65% moisture, you start getting a whole tree of other reactions occurring. And these are the degradation, the fermentation reactions. And they're producing a range of other products like glucose, fructose, ethanol, dextrans, reducing sugars, and other degradation products, all of which you pretty much don't want because the only thing you really need out of the sugar cane at that point is sugar and fiber. So, yeah, that's not desirable. And also, it makes it really hard to model because you're going from make two reactions that you're trying to model, which is quite easy to do, but then you've got a tree of all these other competing models all over the top of each other. It really complicates, it just basically adds noise to the prediction. On top of this, the pole method itself assumes that 100% of the optical rotation that you see is due to sucrose, which works when you have a healthy cane, but when you start having fermented cane, you see reducing sugars like fructose, glucose, dextrose, all a whole tree of reducing sugars, which all have their own optical rotation that isn't the same as sucrose. So that makes that causes an issue with the pole reading itself. But that said, pole is the certified method, so the NIR pole predictions have to be aligned with the lab validation pole, as per the usual usual validation process. But this will also kick on to other pole related constituents such as pollen cane, CCS, and purity. So this is an example of one of these lines in the tree of fermentation products by one bacteria. And these are all the different fermentation products that you get from this reaction. And you can see all the different polar rotations, optical rotations, I should say, of these different constituents. So all of those are making it difficult to get a good pole reading when you have fermented cane present in the supply. So that's the lab method issues, but the NIR has an issue in that, okay, we're trying to match the lab. If we try and represent the fermented cane in the calibration, then that has a disproportional effect in terms of error on the rest of the supply. So 95% or whatever your percentage of healthy cane that's in the calibration for that year will, if we try and introduce fermented cane into the calibration, will have a worse error than they should otherwise have. And it's disproportionate. It's a bigger increase in error than the population that you're adding. So traditionally the answer to that was to remove the fermented cane from the calibration, but that means that we're probably giving you an exaggerated pole for fermented cane because it's underrepresented in the healthy cane calibration. So what would be nice if we'd be able to have more than one calibration that has one for healthy cane and one for fermented different levels of fermented cane. If only we had a way to do that, because at the moment, our current software only can do one calibration suite at a time. So that brought us to developing the multiple calibration method. So here we have a scan, and the first thing that happens is it hits a classification equation. So we apply a classification equation to determine which of these three groups it is in. So juice, beer, or wine. So unfermented, partly fermented, very fermented cane supply. And then we've made a calibration structured off only this sort of cane, this classified cane. So healthy cane, moderately fermented cane, and then very fermented cane. So that means that we get the scan result, we tell you what sort of fermentation you've got, and then apply the appropriate equation and give you a result. So no post-processing, it just goes through the line like that and give you a result. and also gives you a chance to match the lab and counteract this fermentation problem. So we've done desktop study on this to see how well it would actually work. We use both Unscramble and R as the prediction models. SMV classification for the classification equation was very good with very good accuracies and precision, and also recall. And then when we applied the corresponding calibrations, we saw an improvement to the error for pole by 36% and CCS by 40%. So it's definitely worth doing. So we also did some testing late last year, but probably a good problem to have, but there wasn't much fermentation in that cane supply, so we didn't really test the model that much. So what's going to happen this year is that we have 3 systems down in New South Wales, and we're going to be running them in tandem with the current method. And once they're up to speed in terms of performance, we can consider changing them over. The Mulgrave instrument that we ran last year, we're also running a similar experiment there, with the difference being that we're going to try a new software, a new FOSS version of software, which is the instrument manufacturer, just to test that out as well. So once we've developed our software to the point where we're happy, hopefully by this time next year, we'll be rolling out new software to do the fermentation multiple model calibration approach. But what this also allows you to do is, if you say have something like RSD or another model that you want to apply, it means that we can now do that, because we'd still needed to be able to have a multiple calibration suites in the software capability to be able to do that. So it's another reason why we need to do this software upgrade. And yeah, it should be interesting and give us a better prediction on this issue. So thanks for your time. I would like to open to questions.
Thanks, Joel. That was a very captivating presentation. And
Nice.
I guess now a lot of people want to have questions. So if you do have a question, you can type it in the Q&A box or raise your hands located on the top bar, and you will need to unmute your microphone to ask a question when prompted, and then mute your microphone again. So any question?
Yep, I think I can see a
Yep.
raised hand.
I didn't see a raised hand, but I've got William.
William, yep.
William's got a question.
I think you might be on mute still.
No, it's fine. William, would you ask your question?
Okay.
Thank you.
Good afternoon.
G'day.
Thank you for your presentation, Joel.
No worries.
I'd like to know if you can comment on the use of NIR to identify other components than sugarcane quality. I know that there is some work being done to try and correlate NIR spectra with raccoon stunning disease, for example, the presence or absence of the bacteria.
Yes.
There's also some interesting work out of Sasri in South Africa where Stuart Rutherford was trying to correlate NIR readings with smut susceptibility or in sugarcane varieties. Could you comment on those 2 issues, please?
Yes, absolutely. Yeah, so raccoon stunting disease, we're currently working on that at the moment. And yeah, it's definitely challenging, but because you're not really predicting on the genetic aspect of the disease. What you're really predicting on the compositional change or like the symptoms of the disease. You're not seeing the genetic signature of the disease. You're testing. It's like if you go to the doctor, you're going in there. You say, I've got a sore throat, a stuffy nose, and whatever. Then they say, oh, well, you might have this, and then they do further testing. So that's kind of the goal with the RSD calibration, is to just really narrow down So rule out, it's like a yes, no, do you have RSD? Yes, no, maybe, do you have RSD? One of those classification equations we talked about before. And yeah, so you're really just looking at compositional changes that are repeatable for that specific disease, which is challenging, as you could probably appreciate, because NIR typically doesn't go much below parts per million. So at that point, you're really looking at a repeatable compositional change in other things. Does that answer your question? So yeah, we're definitely looking at that. And it's
Yes, I
progressing.
want to know actually how accurate has that estimation been so far?
It's so sometimes yeah, it's still in development is what I'd say. It's getting close though. It's about the other problem is you're also up against what's the error of the primary for that as well. So yeah, for a 50-50, you'd want an error to be pretty good. In the primary, it's okay, but that means that we're up against a pretty tight wall for the error for the NIR. So I can't really comment just yet on where that's the final answer for that is, but it's definitely happening. It's looking pretty promising though. I can't give you probably this time next year we'll be able to have an answer for you for that.
Thank you.
Thanks,
Okay.
Joel. So there is a question from Zahid. How many mills in Australia or in other countries are using NIR?
Oh, that's so we deal with a few different countries. We've had NIRs in Vietnam and Fiji for a bit. They don't have it anymore. Brazil heavily uses NIR. They have like more mills, so they have more opportunities for NIR over there. So yeah, I know they have like 100 in Brazil at least. Depends on the type though. As I mentioned, that like, there's different methods that you can use the NIR for. Like so, a lab versus a production versus a handheld versus yeah. So there's different ways, and I think they tend to use more lab as far as I could tell, and we tend to use more process. But yeah, it's very widespread.
All right. There is another question from Jake Humphrey. The micro NIR and the online instruments are use different wavelength ranges. Have you been able to combine the data from these two different instruments types into RSD and other modeling, or do you have to remain as separate models?
You can. It's tricky because what that's called transforming the equation. So you're basically using maths to try and align the spectra up because they have different spectral wavelength regions. Um, but in terms of what we use diode array instruments on the mill, and they have a pretty similar wavelength region to that of the handheld. But I think we'd still probably do handheld calibrations as well. Basically, whenever you do a transformed equation, you typically use that as a base, and then as soon as you can, you replace it with actual spectra from the instrument that you're using. So yeah.
There is a question from Mathilde. Thank you for this interesting presentation. I have a question about CAN predictions, especially with SpectraCAN. What kind of regression model do you use? Do you use classic PLS regression? Have you tried locally weighing PLS regression?
Yeah, we've tried a few different ones. Often we find like we've lots we support vector machines. We've used all sorts of different calibrations in the past, but we still land on the usually simplest is best in terms of it's easier to get at the methods that you are applying. So you could use even AI methods, but that is harder to tell what it's doing. So yeah, we prefer traditional principal component analysis, PLS regression. But depends on the purpose. Actually for discrete equations, we tend to use support vector machines.
Does that answer your question, Mathilde? I'll let her answer. So there is a question from, yes, She said yes. That's good. There's a question. Hi, can you please share a video or presentation of practically performing cane analysis using NIR for bricks ball fiber? Thanks.
A video of it, for what sort of instrument? So like for a handheld, you basically get for the stalk stuff I talked about before. This is actually the dibbler. I don't know if you saw that before, but so assuming this is the stalk, you basically in those two sample points I talked about, you put it right up against the stalk. You don't even need to really worry about the stray light, which we considered might be an issue, but you can build it into the equation and it doesn't really add that much noise. So just straight on the stalk like that. In the third from the top, third from the bottom, and then you average it. So that's basically it. Yeah, does that answer your question? That's for the handheld. For NIR, like for online, it's actually on mill number 1, and it's fixed inside the chute with 1.5 meters of cane above it to put pressure against the sample point so that you push out all the air gaps. So it depends on what you're doing, is the short answer.
Thanks, Joel. There's a question from Fabrice Davrieux. Have you done a calibration for bricks using micro NIR on fresh sugarcane? If yes,
Yeah.
are you happy with it?
Yeah. Yeah, no, it's quite well. That's actually the one I showed before. That maturity calibration, the basis is bricks because it's the easiest one. So then we apply the maturity model and then get more than just bricks. You get the whole story with the maturity model. But yeah, and it's quite good. We're happy with it. We're actually making live decisions out in the paddock already with it.
William, do you have another question or your hand is still up? Well, while I'm waiting for William to see if he's got another question, I just do have a question. So,
Sure.
how much does it actually cost, like to get
I can't turn off my hand.
Oh, okay.
No worries.
Okay.
All good.
So, how much the portable unit cost, and
So
does the calibration come with, like, come with it? Like anyone can actually have that and then do it and actually look at the data and analyze the data and get some results from it?
So at the moment, the VRV ones, they cost 50 grand plus 5 grand for the this is Australian dollars for the model for the prediction engine that we use. VRV has their own prediction model that I guess you don't pay the 5 grand for, but we also develop our own calibration. So if you were to go up and buy it from the shelf, you'd still need to be able to do that whole validation calibration because that's that 55 grand isn't the real cost. It's the lab, the lab work and the field work to get the samples to make the calibration and the calibration work to get the model. So it's not quite such a simple thing as just going to the shop, buying one, and then going out in the paddock. There's a few steps in between.
Indeed. Fabrice has another question. Thanks. Did you try NIR on sugar?
Yes. Yep. We've done it online and in the lab, and yeah, it works quite well.
There's another question. Hi, Joel. Thank you for your presentation. I have a few questions. I'm from Vietnam. I've analyzed indicators like pole and bricks in juice and molasses. These values vary between sugarcane seasons, making it difficult to build a stable calibration model, as the range this year may differ from the last. Have you encountered this issue before? If so, could you share any advice? Thank you.
Yeah. There's two schools of thought around how you handle variation for NIR as a secondary technique. Either you could do what the pharmaceutical industry tends to do, and they have, because they clean everything up with stainless steel, it's clean, it's as clean as possible sample that you can get, and that's how you deal with the variation. You just physically remove it. The other option is to build it into calibration. When you do that, though, the cost of doing that is an increase in error. So that's the tricky part of calibrating is how do you deal with the appropriate amount of error and how much error are you willing to wear for the number that you want to use it for. So to deal with varying supply like you're talking about, that's how I'd deal with it, but you'd just have to be a bit delicate in how you deal with that variation.
Hey Joel, do you have what advancements in NIR technology are you most excited about for like the next 5 to 10 years?
Well, at the moment, we've got a lot of work for this one planned, so that'll keep me busy. Um, but also just even online and just it's not just the technology, it's what you do with it that really gives you value. If you can have it, an NIR can be a very costly brick if you don't do anything with it. So it's really what you do with the numbers that makes it valuable. And we have had cases where an NIR paid for itself within the first use of it. So depends on the multiplier of the thing you're making the decision around.
Mm, yeah. So I just had another question.
Sure.
So is there like a lot of so what's the correlation between the NIR, the portable one, and the benchtop one? So like is the correlation very close, or anyway that it's in your calculation and
Yeah, they're pretty, they're sort of close, but they're also very different data collection methods. So we've got a linear variable filter versus a diode array. Um, and depends on the application too. We have another linear variable filter that's probably closer than because it's the same. It's a VRV. It's basically the same instrument. So that would be our first choice if we're going to try and bridge calibrations. Is get the instrument that's similar. You can bridge calibrations using different wavelengths. It's just tricky, and you tend to want to only do that as a last resort or really a first resort until you can get something better, which is the actual instrument data.
and so yeah, okay. So I guess the calibration have been adapted for early maturity cane and late maturity cane,
Yeah,
and yeah, and um, I had another question, but George has put his hand up. So
sure.
George,
Hi, Joel. Thanks for a great presentation.
No worries, thanks.
Probably following on a little bit from what Natalie's just asking, I'm pretty excited about how we could apply this in the breeding program.
Yep.
And I'm just wondering whether the calibrations that you've built into it are based on the bricks and the maturity model.
Correct.
And
Yep.
as you know, SpectraCane has different calibrations.
Yeah.
So if we want to apply it in the selection program, do we need to can we use the calibrations that you built into the micro NIR, or do we need to calibrate it to the SpectraCane, which itself is calibrated to the juice lab?
I'd say it'd be that interim position where you'd first probably try and calibrate the SpectraCane and then build it from there. I'd say that yeah, you could try bridging. You could actually try using it directly, like using the secondary as like a tertiary sort of method initially, just to build up some samples until you get the actual lab results. For this, like, so you could use the results from the SpectraCane to calibrate for the handheld in lieu of the actual lab data until you get it, but you'd eventually want to do that. So I'm not sure. I'd say it's probably depending on what stage of the growth that you're looking at. It might actually be outside the range if it's like suckers, sort of like, new growth, really new growth. But, build it in. That's how we do it. So I'd say it's probably pretty good. What we've got now for the maturity for the cane stalk's probably a good start anyway.
Thank you.
Yep.
Joel, you got another question from Mathilde. She has
Sure.
a precise question. What is the reference that you use in order to evaluate the bricks in micro NR?
The reference. Okay, yeah. So bricks, so we actually use refract bricks using a dibbler and the so juice, basically juice bricks. And that's a refract, but it also works for we've calibrated the bricks refract to the old optical refract as well, just to make sure we're all getting the same number. But also on top of that is that the maturity model was derived from online data as well as mill laboratory data. So all these things have been used to validate it. So it's probably one of the most validated things out there because, as I said, the mill gets 10,000 scans a day. So we do that for all our mills, and the relationship holds for all that. In terms of the handheld though, yeah, we just use brick refrac. Does that answer your question?
I'll let. Yes, thank you. Joel, I've got like maybe a last question, and then I'll see if someone else has the last question. So, do you think that if you were to use the same hand the portable machine, and you will use it in other canes in somewhere else in the world, would you think that you get the same data, or you think that maybe there's some components that we don't find here that will actually kind of twist the data that you have yourself?
It's possible, but we've already kind of done that twice with Fiji and Vietnam, and it just all lined up. So I think that actual curve, I can't prove it, but I'd say that actual curve is part of the genetics of the cane plant itself. And I wouldn't be surprised if other crops have their own curves that do a similar thing.
Okay. There is another question from Jake. You mentioned the overinflated pole in fermented cane is difficult. Do you think this pole is overinflated due to error in the primary pole method or NIR itself? And
Okay.
secondly,
Yep.
Secondly,
Sorry.
if the error is in the primary pool method, do you think the population classification method you are working on for the fermented will be effective? Cheers, and thank you for the great presentation.
Too easy. Yeah, so the answer is yes, it's both. So the primary method poll, basically the error exhibits as an increase, so like a shotgun sort of spreading of the error up the top end where the fermentation is occurring. So that's the first problem. NIR can't fix that problem. That's a separate problem. That's a primary method problem. But what the NIR can deal with that we currently have a problem with is in that population structure that will line up our top end results to line up with the lab results. So I think the center of that shotgun is probably pretty good, but the so our data will line up with that center better is the answer. So it still will increase the accuracy of the method, but yeah, the poll itself has its own inherent issue.
Okay. So I think we don't have any more questions. So well, I just wanted to really thank you again, Joel, for today's presentation. I think we all agreed today that we'll learn a lot on near-infrared technology. And actually, it's quite exciting for the future for me, like phenotyping and I guess plant breeding. I just wanted to thank you all for your attendance today. I hope you have enjoyed today's webinar and that you will join us at the next SRA webinar coming soon. For information on the webinar, please visit the events page on the SRA website. Thank you very much. Thank you, Joel, and have a great weekend, everyone.
No worries. Thanks everyone. Thanks for your time. See you.